Greetings or good afternoon, depending on where we are. We are proceeding with our lectures in thermodynamics. My name is Professor Duke Orata. Today we want to look at what we call Prandtl and Taylor's modification of the Reynolds Analogy. Remember, we derived the ratio of the heat transferred to the shear stress based on Reynolds Analogy. And there are several things which we had assumed there. One, in the Reynolds Analogy, just in passing, the Reynolds Analogy we assumed that 1 alpha was equal to V. And what is alpha? Alpha is thermal diffusivity. And V is kinematic viscosity. That was one of the assumptions which we made, which was fundamental in that approximation. Number two, we chose the boundary. We chose the boundary to be, as we have our x, we have our y, and it's just the boundary layer. The boundary, remember, we have sigma, the velocity boundary layer, and we have the thickness of the thermal boundary layer, and we have the free stream. And we had assumed that the distance there was L. So we took our boundary for the integration as from z, the integral, that is du, we said it was from the integral of 0 to L, that's where 0 is at the wall there. We assumed that was tau y over rho over V plus eta. And remember that eta is eddy diffusivity. And in terms of heat, took the change in temperature to be the integral minus q dy over rho Cp into alpha plus eta. And remember this is eta is eddy diffusivity with respect to the heat transfer, and that is eddy diffusivity, that we call eddy diffusivity. So you can think of that like as eddy diffusivity to do with the heat transfer. And we took the boundaries again to be 0 to L. And like we have said, we assume that alpha, we assume that alpha is equals to V in this particular system. And those assumptions are a bit of a challenge, because that's what led to this modification. Why we are modifying the Reynolds analogy is to think of it that, remember, in the flow, in your flow, whether it's in a turbulent process, there is a sublayer of laminar flow. Always remember that. Even if you're in a turbulent layer, remember in the turbulent layer, we talk about turbulence as the result of velocity gradients within the fluid, which create eddies and so forth. We have mass transfer, we have transfer of momentum, and so forth. We have discussed those in our earlier lectures, and I encourage you to look at those and look at the lecture on Reynolds analogy, where we derived all these expressions. So we're just moving fast. So we have the sublayer where we have a laminar flow. So what does that mean? If we say that the thickness of that sublayer is sigma b, then we can now say that the limits for these two integrals should not only include this, it should have the layer where we have the turbulence and the layer where we have the laminar flow, that sublayer which we have there. So we have two layers. We have the sublayer for the laminar flow, and we have the turbulence layer. So in that particular case, therefore, it means that in place of 0 starting at the wall, then we will have sigma b. We'll have sigma b. So if we incorporate the laminar sublayer Then the boundary now will be from y is equals to sigma b to y is equals to L. And secondly now, we don't assume that the kinematic viscosity is equal to alpha. Secondly, similarly, we are saying it's not equal to V. But look at it this way. This does not affect us much. This does not affect us much. So that even if you're working in the turbulent layer, remember we have alpha. So this does not affect us. Not affecting anything. Why? Because if you're working in the alpha plus eta, look at alpha plus eta, and you also look at rho Cp, alpha plus eta, what we are saying, even in the turbulent layer, always remember in the turbulent layer, then this ED effects will be greater. So we expect ED to be much, much greater than alpha or V. Sorry for that, V. So it doesn't matter. So we are still okay. And then, of course, remember when we did the Reynolds analogy, the Prandtl's number was 1 for the fluid. PR was equals to 1. Now it will not be equal to 1. And what is Prandtl's number? Just remind ourselves that Prandtl's number, PR, is mu Cp over K. Again, that is dynamic viscosity, that is isobaric heat capacity, and that is thermal conductivity. Now let us proceed. Let us put in these aspects of laminar flow. Let's now put in these aspects of laminar flow. So for laminar flow, these integrals now become du is equals to integral from sigma b to L tau, which tau, remember, is the shear stress, plus eta, and for dt will be minus q, dt will be minus q dy over rho Cp plus into alpha plus eta sigma b to L. And so when we solve them, the same way which we saw in which we solve the Reynolds analogy based on all those same assumptions, what are we saying? We will get basically similar results. So we add q over tau, where we assume q over tau is the same as q. Now it's qb tau b. Remember, we're now talking of sigma b. So we will get exactly the same results, and that will be qb over tau b Cp will be theta s theta b us minus ub. Remember now, we are not using y is equals to 0. We have said y is the equivalent of the thickness of the sublayer having the laminar flow. And then number 2 of importance also now, remember that for laminar flow, the velocity gradient is constant. In the laminar layer or sublayer, the velocity gradient is constant. Similarly, remember in the laminar layer, the heat is transferred by conduction so that the temperature gradient will also be constant. The velocity gradient will be constant. Remember Remember, the velocity gradient is du dy, and the heat transfer is by conduction, and therefore temperature gradient will also be constant. What is temperature gradient? That's the temperature gradient. Those are very important. So working on that, then we know that basically our tau is mu du dy, and that of course will now be mu. We have mu du over dy. Mu is the dynamic viscosity, and this quantity will be ub over sigma b. And similarly, q will be minus k d tau dt dy, which will be minus k into theta b over sigma b. Very important. Now, when we're working in those quantities, if we divide 1 and 2, 2 and 1, 1 and 2, 1 and 2, so dividing 1 and 2, we have that q over tau will be equal to minus k theta b over sigma b divided by mu ub over sigma b, and this will simplify to minus k over mu into theta b over ub, q over tau. And so if we rearrange this particular equation, let's call that our equation 3. If we rearrange, let's call that 4. If we rearrange 4, rearrange this equation 4, that's cross multiplying, then you see that QB over TBCP will be equal multiplied by US minus UB will be simply theta S minus theta B. And so theta B will simply be, take theta B, that will be minus theta B, QB minus that, so we multiply the minus signs to remove the negative sign, will be theta S minus QB over TCP US UB surfaces. And so let's call that our equation 5. So we now just simply take the value of heat, that boundary, and so we have here theta b. On rearrange, if we rearrange equation 3, we have theta b is equals to q over tau mu over k ub minus. So we have just rearranged theta b, that goes q over tau times u over k, u over k ub. And so let's call this equation number 6. So if we substitute this 6 into 5, if we substitute it there, we will have now minus q over tau mu ub over k is equals to theta s minus q over tau cp into us minus ub. Let's call that expression number 7. So we have just substituted this in place of that. So now we can work and try to simplify it. See what are the outcomes. What are our outcomes here? So first of all, if we go about it is the way we want to do it. It's very, very straightforward. So what do we want here? Want minus q over tau. Minus q over tau. You can collect them all together. Minus q over tau into mu ub over kappa over k is thermoconductivity. Then we have this quantity there. We have plus q over tau Cp US minus UB. We have just added, we have taken it the other side. That will be equal to theta S. So we can cross multiply to remove the heat capacity. So we'll have minus q over tau mu UB over k Cp plus q over tau into US minus UB is equals to Cp theta S. And there's a reason why I've done that. Remember that you can clearly see that mu Cp over k is Prandtl's number. Note again, once again, that Prandtl's number is mu Cp over k. So we can plug it in there. So we'll have minus q over tau, Prandtl's number, which is that, and that, UB, plus q over tau, that's minus q over tau, that is plus US minus q over tau UB is equals to Cp theta S. And so as we continue with the simplification, now it's just straightforward algebra. We're just moving, simplifying things. We are seeing the B's are common, so we can pull it out. So we can have Qt minus Qt tau UB into Prandtl's number plus minus 1. We are taking this quantity. So we just pulled out Qt UB and Qt UB there. Plus Q over tau US is equals to Cp theta S. Cp theta S. And of course, we can pull out the Qt and take the other bulk, the other side. We can pull out the Qt's so that this will now be, if we remove this sign here, that will be 1 minus PR. So we have Qt, don't get confused, UB into 1 minus PR, just remove the negative sign, plus Qt, Q over tau, sorry for calling tau T, US, is equal to Cp theta S. On further simplification, we can now pull out the Q over tau. That becomes now, we can actually divide through out by UB, dividing, we are trying to simplify it as much as we can by UB. So we have Q over tau into 1 minus Prandtl's number plus Q over tau US over UB is equals to CP theta S over UB. We are getting there. So Q over tau into 1 minus Prandtl's number